Hello, my name is Mario de Haro Marti. I'm the extension educator in Gooding County in Idaho, serving the Magic Valley. And today I'm going to talk about the effects of composting dairy manure with the addition of cleanup zeolite, zeolites, and what effects that has on the ammonia emissions and nitrogen speciation and the compost maturity and stability. The take-home message, the take-home points are that the on-farm co-composting of the dairy manure with the cleanup zeolite has an overall positive effect on the final product, on the final compost. Um, there is, in our study, there was ammonia and other emissions were reduced. And the compost with the zeolites have a much higher stability, quality, and available nitrogen as nitrate than the regular dairy compost. Also, that because of that, this compost can be sold at a higher price for high-end uses. So just a reminder, this is a previous study on ammonia emissions from compost. Ammonia emissions are a natural, I would say, effect of the composting process, especially when we don't have enough carbon to balance the equation on the carbon to nitrogen side on the compost, um, on the feedstock. And we live in a desert, so we don't have many carbon sources, and we are a dairy producing area, so we have plenty of manure, which is rich in nitrogen. So we lack the carbon to balance that equation to the carbon to nitrogen ratio that reduces emissions that should be over 30 to 1. 30 to 35 to 1 is ideal, and that reduces ammonia emissions. But we cannot get there for most of the year. Another thing that also changes ammonia emissions is the management of the compost management during its production. And we know that there are diurnal and microclimate, depending where the windrows are located, emissions variation as shown by this graph on the warm season and the cold season on the ammonia emissions from composting. So in this project, what I did is add clinoptilolite zeolites into the composting mix. This study was done on farm, so this is beyond the lab with farm with the manure directly from a small dairy farm, and using a tractor and windrows, and we measured the emissions from them. The clinoptilolite is mined in Idaho. It's a local resource. We mix the manure on different stages of aged manure, fresh manure, with some straw available on the farm, as any dairyman gonna do when they have those available. On the that was our control windrow, and the same mix with the addition of the zeolite was the treatment windrow. We didn't have a compost turner, so we turned the windrows with a tractor. We corrected with moisture at the beginning and during the composting process. When we turned the windrows, we measured, we did a squeeze test to measure the moisture on the field, and if we felt that those windrows need water, we added water as required for a complete and true composting process. And the average composting time was 149 days on those windrows, and we screened the windrows before sampling. What we measure ammonia emissions using Ogawa samplers. It's a sampler that measures the concentration based on a pad that is embedded in a solution. We did complete nutrient analysis as a complete compost nutrient analysis for nutrient management, including all the metals and all the components that usually the labs can handle here. And temperature, we recorded temperature, you can see here, with a thermometer, a dial thermometer, and also we use data loggers. We did other perception. We have a spreadsheet with operators and researchers every time we turn a windrow and we take samples. We take note of the other scale perception we have. We measure the volume reduction on the windrows and production parameters like the percentage of refuse you can see here, for example, in this picture. The machinery use, hours of tractor use, labor, and other costs. Here is some pictures of the Ogawa sampler location. We put these chimneys, and the Ogawa sampler was located about this height on a stake that was inside. The chimney was just resting on top of the compost. It wasn't inside. So any circulation of air inside the compost could go through the chimney freely. Again, here you see the thermometer and the data loggers. Actually, data loggers, half of the study started failing. So our backup plan on the regular thermometer is the one that we got most of the temperatures, that we use some of the data loggers too. So what we found on ammonia emissions is that the overall cumulative reduction was about 14%. And what you are seeing on the graph is we measure on the first, when we build the windrow for 3 days, 3 periods, and then on the other first turns. So here is the building, what we consider the first turn, the building of the windrow, the second turn from 4 to 6, and then the third turn, 2 periods we measure on the third turn. We didn't measure on the 4th and 5th turn. So on that we got 14%. But if you see the curves here on the blue dotted line, this one is the control, and the red one, the curved line, is the treatment. So we estimate that the total ammonia emissions reduction is around 20 to 30%. And again, there was a perceived other reduction. So the treatment windrows also have a reduction on ammonium in the mix at the beginning and at the end. So you can see here, even on the in blue, on the ammonium before, this is the control, and this is the treatment, is much lower just from the start. Again, we have a small dilution effect by adding the zeolites. But what I believe is going on here is that the zeolites, the cleanup zeolites, started absorbing, and other studies have the same results, start absorbing the ammonium right away when you mix it. This is again was on farms, so the whole process of mixing the windrows, the different manures with the straw, with the zeolites, building the windrow with the tractor, and until we took the sample took about 6 hours. So per windrow. So in those 6 hours, we see already a reduction in ammonium. At the end, there is not much difference. This is not a significant difference at the end on the amount of ammonium, but there is a noticeable difference, 3 times more on the nitrate side. So the treatment has 3 times more nitrates than the control. So that speaks of nitrification processes that happen thanks to the presence of zeolites in the compost. And there was a tendency to a lower carbon and total carbon and carbon to nitrogen ratios on the treated windrows that also speak about the use of all the carbon available that wasn't matched. Another test we did was the Solvita test. This is a maturity, carbon respiration maturity test that is designed to be done on the field. We did it in the lab. But what you're seeing, the first 3 rows are the control, and the last 3 are the treatment. You can see a noticeable difference, especially on the maturity index, the compost condition, the phytotoxicity, noxious hazard, and the ammonium estimate, and the nitrogen loss potential. So the regular compost is still shows an active or curing process. When the zeolite compost is a finished compost, it has more oxygen depletion and less phytotoxicity and noxious hazard. So the nitrogen loss potential is almost non-existent. So that again simulates what happens when you have a well-balanced carbon to nitrogen ratio and high-end compost on the treatment, and our regular dairy compost on the without carbon correction, carbon to nitrogen correction on the top. Other things we observed was that the treatment windrows have there wasn't easy difference between the control and the treatment, but the electroconductivity difference was significant in the treatment between the initial and the final. So there was kind of immobilization of salts, if you want. The phosphorus and zinc showed a tendency of reduction on the treatment, and all the other parameters, except the ones I already mentioned, there were no significant differences. The volume reduction using a tractor wasn't that big on this case. It was around the 21–23%, and it wasn't significant between the treatment and the control. What it was significant again was the odor rating between treatment that was much less than the control. And the refuse at the screening also was not significant. The difference was dependent mostly on the moisture of the windrows and not if they were treatment or control. In conclusion, the cleanup zeolite zeolites have a very positive effect on the final compost characteristics, which allows us to use the zeolites as replacement or complement to the carbon addition to balance the equation on that initial composting feedstock. And in this way, we are using two local resources to generate the new high value local resource. So we use the cleanup zeolites that are mined in Idaho with the manure that is produced here in the Magic Valley in Idaho, and the new product, the compost, have a higher value. Because it has a higher value, because it shows higher quality, higher maturity, that make it usable for industries that usually they shy away from direct dairy compost. The dairy compost is a very good nutrient source for extensive agriculture, alfalfa, corn silage, cereals. But some industries like landscaping industry, greenhouses, high value crops like fruits, berries, etc., they sometimes shy away. In this case, with this, they have the stability and the maturity on the compost to use it. And that comes with a higher price tag too. There is an evident reduction on ammonia and other emissions that also are needed in the industry. And again, the higher nitrate content is something that those industries I mentioned on the higher end are looking for. And not only on the Solvita, this is backed up by the lab results on the nitrate to ammonium ratio. So again, this could be sold at a higher price, and we didn't find any negative effect either on the production side of the compost during the process or on the final product. I want to thank our funding sources. It was a USDA Conservation Innovation Grant. And thank you to the co-authors and the producer, especially that host this on-farm research. Thank you, and let's open for questions.